Assalamu alaikum. Welcome again to this video, which will be about the neuron simulation using Python. So this video will be following the previous two videos that we have seen before. In these videos, we have talked about simulating the injection of a current and recording the voltage of the membrane and the injecting or the clamping of the membrane potential and recording the currents of both sodium and potassium that flow through ionic channels in the neuron. In this video, we will be expanding our simulations to two neurons. We will be creating two neurons and we will connect them via a synapse, and we will measure the effect of synaptic input on the postsynaptic neuron. So as usual, we will start our simulation by importing the necessary simulation environment. So from neuron, we will need to import H and GUI. Okay, so H gives access to neuron simulator and GUI for graphic user interface. And we will also need to import matplotlib. Sorry, import matplotlib.py plat as plt. Great. Now that we have imported our necessary simulation standard libraries, we need to create our two separate neurons or sections. So we will call the first neuron the pre-neuron for presynaptic neuron. This pre-neuron will be H dot section, our section, and we can call it or name it as simple as we did before, pre-neuron. As I said, we will be creating two neurons in this video. The second we'll call it post neuron, and we'll name it post neuron. Great. Now we imported the libraries, we created our two neurons, and now for each neuron, we will set the dimensions, the length, the diameter, and we need also to insert the ion channels through inserting HH or Hodgkin-Huxley model. So to do that simultaneously or in the same time for both neurons, we can use a for loop. So for sec n, and let's type in here pre-neuron, comma, post neuron. So for section in these two, we will set the section or the sec length to be equal to the sec dot diameter diam, and we will set them as we did before to be, for, let's say 20. And we also need to insert the model sec dot insert Hodgkin-Huxley. Great. Now for both our neurons, we set the length and the diameter of them to be 20. We inserted the model, which means inserting ion channels. These ion channels will be necessary for generating action potentials. Now we need to make the presynaptic neuron fire, and to do that we simply need to inject a current with the right amplitude so that the pre-neuron can generate action potentials, and those action potentials would have effect on the postsynaptic neuron through the synapse that we will be creating later on. So now let's create our simulation, which would be H.I clamp for clamping the current or injecting the current. We will be injecting the current in the presynaptic neuron only, not the postsynaptic. We'll inject it in the presynaptic neuron, exactly in the middle of our pre-neuron. So now let's set our other parameters. Let's set the delay to be, let's say, 5 milliseconds. This stimulation or this injection of current will be delayed 5 milliseconds. And let's set the duration of stimulation. So stim, that's dur. Let's set it to be, for example, 2 milliseconds. Great. Now let's set also the stim amplitude, stim.emp. This would be in milliamperes. Let's set it to be, for example, 0.5 milliamperes. I think that would be enough for triggering the ion channels and causing an action potential in the presynaptic neuron. Now, great. Now that we have created the pre-neuron, the post-neuron, and injected the Hodgkin-Huxley model in both of them, and applied the stimulation or apply an injection of current in the presynaptic neuron, what we need to do next is create a synapse. And to do that, we'll type in sign for synapse, and we'll call it H dot AXP to sign. So in neuron, there are multiple types of synapses. The one we will be using here is the exponential synapse. And this exponential synapse has two time constants for the rise time constant and the decay time constant. Now, this synapse will be created in the post neuron. So the post neuron is the neuron that will be having the synapse. Now, let's type in. So X to sign, I'm sorry, the S here is capital. X to sign. Post neuron. Post neuron. Let's say in the middle of the neuron again. Let's keep everything in the middle. This creates a double exponential synapse at the midpoint of the post neuron. Now let's set the parameters of this synapse. So let's say sin tau 1. Let's set to be 0.3, for example. You could play with these parameters as you want and explore the results yourself. So this time constant we set it to be 0.3 milliseconds, and let's create a second time constant sin to tau 2, and let's set to be the decay time constant. Let's set to be, for example, 2 milliseconds, and we need to set the reversal potential in millivolts. So the reversal potential in millivolts, let's set it here to be like minus 13 millivolts. So what do we mean by the reversal potential in millivolts? Is the potential that will be created by this synapse. So if this synapse is activated, it will set the membrane potential to be minus 30. For this excitatory or for this reversal potential, we can make it to be excitatory for excitatory synapses, and we can make it to be inhibitory for inhibitory synapses. So for this example, we will be setting to be excitatory. How do we know it's excitatory? Minus 30 is above resting potential. So if the membrane voltage is set above the resting potential and above the threshold of firing, it is an excitatory. And if it is above the firing threshold, it might cause an action potential in the post synapse. If it is above the resting potential, it will be excitatory. It might or may not cause an action potential depending of of the value that we set here. If we want it to be inhibitory, we can make it to be less than the resting potential, less minus 65, we can make it minus 75, minus 100, etc. We will make it less than the resting potential, which means we will bring the membrane potential more and more negative, which will make it far and far from the threshold of firing. That will make the neuron less and less susceptible to be given an action potential. I'm sure you recognize these things from the neurophysiological properties of neurons and synapses and the types of them, excitatory and inhibitory synapses, which are dependent on various things, including neurotransmitters. But in here, we will be just setting the reversal potential. This reversal potential will determine if the synapse is excitatory or inhibitory. Now, enough with the talking about synapse. Let's dive into details. Now, we need to create a NetCon. This NetCon will connect the pre-neuron to the synapse of the post-neuron. NC equals H dot NetCon. We will connect, as I said, the pre-neuron, the middle of the brain neuron, this voltage, so that's ref, I'm sure you remember this ref V. We will connect this to our sine and via our pre-neuron. Sec equals pre-neuron. Now, typing in this line, we have connected our pre-neuron to the synapse of the post neuron. Great. So the pre-neuron 0.5 references the membrane voltage of the midpoint of the pre-neuron. The sine reference to the target synapse. So in other simulations, we might have different synapses or multiple synapses, and so we have to determine or to specify the synapse that we want to target. And the sec equals pre-neuron explicitly say the voltage reference comes from this section. Okay, so this section is the section that we will be using to read the voltage. Now, what is NetCon biologically? This NetCon mimics the event detection system. When the membrane potential of the pre-neuron crosses a certain threshold, an event, a spike, is triggered, and the synapse is activated, causing a neurotransmitter release. But here in our simulation, we have no neurotransmitters, no not of course a lot of things. But we can mimic that using the NetCon. Okay, great. Now let's set our threshold of our NetCon. So NE dot threshold equals minus, let's say 30. Great. Now this means that the pre-neuron's membrane potential crosses minus 30 millivolts, an event is generated. An AP or action potential is detected. Now we need to set the synaptic weight and NC weight. 0 equals, let's say 0.02025, for example. This synaptic weight, it's the synaptic strength or the weight of our synapse. The higher it is, the stronger the postsynaptic response is. The higher the weight, the stronger the postsynaptic to the presynaptic event will be. Let's set also the delay. Let's set to be 1. So the delay in milliseconds is the delay between the presynaptic spike and the synaptic activation. We consider to be another value. I just chose here Now let's analyze what we have done so far and see if we have made some mistakes or if everything is good. Now, we imported the libraries, we created the pre-neuron, the presynaptic neuron, the postsynaptic neuron. That's good. We defined the length and the diameter for each one. We inserted the ion channels through inserting HH. Then we applied the stimulus or stimuli, injecting a current in the presynaptic neuron, injecting it in the middle. That's why what 0.54. We defined the delay to be 5 milliseconds, the duration of the stimulus to be 2 milliseconds, and the amplitude to be 0.5, which is thought to be sufficient to give a raise to an action potential. Then we created a synapse. In the postsynaptic neuron, we defined its parameters and we set the reversal potential to be above resting potential, so that would make it an excitatory synapse. And then we connected the synapse of the post neuron to the presynaptic neuron. We connected them using NCH.NetCon. We defined and we set the parameters for this connection, the threshold, the weight, and the delay. Now, the only thing left to do is recording the variables, recording the time, and the membrane potential or the voltage. Now, let's record the time. Let's type in T equals H dot vector. It's a time vector that records. We will need to record it. We record it from H dot dash ref underscore ref underscore t. We will be recording the time. And let's type in also the v pre for v presynaptic to be h dot vector, sorry, h dot vector that records. We will record again, but this time we will be recording from the pre-neuron exactly in the middle of our pre-neuron. Dot underscore ref v for recording the voltage, and we will be doing the same for we will be doing the same for the post synaptic. So v post, I will name it v post, and we will record from the post neuron. Maybe I've gone a little bit faster here, but this is exactly the same thing that we have done. We have done in the previous video, so that's why I'm not giving it much explanation and much time. Now, as you might remember from the previous videos, we also need to run our simulation, and we type in finalize, and we run this simulation starting from the voltage or the membrane potential minus 65. We need to set the time h dot continue, the running time of the simulation continue run. We will continue run, let's say, for 15 milliseconds. For plotting the results, I have already prepared the necessary code for plotting the results here. No need to explain that. It's the same as we did before. Let's uncomment this code and let's run it and see what we can get. Now we have got the presynaptic membrane potential and the postsynaptic neuron membrane potential. Of course, the first one to fire or to give raise to an action potential is the presynaptic neuron, as we injected it with the current, and it caused a postsynaptic the action potential in the postsynaptic neuron, and it was delayed by a few milliseconds, about 1 or 2 milliseconds. Now let's do something else. Let's maybe create or make this synapse to be inhibitory synapse, and let's set the reversal potential to be lower than the than the resting membrane potential. And let's see what we will get. Nice. Now you see that we've got an excitation or an action potential in the presynaptic neuron, but there was no action potential and no depolarization in the postsynaptic neuron. In the contrary, there was a hyperpolarization of the presynaptic neuron. We see here that the membrane voltage uh, went down for a while, and that was because we set the reversal potential of the synapse to be minus 70, 75. And that's the difference between the excitatory and inhibitory synapses. That would be all for this video. I thank you for watching, and as always, let me know in the comments if you'd like to do videos on other topics related, of course, to neuron and similar simulations. In the videos to come, inshallah, we'll be doing more than this. Maybe we can connect more than two neurons, three or more than two neurons, and we see the results or mix excitatory and inhibitory synapses, etc. And we can simulate all those fun things. So that would be all. Thank you for watching. To the next video, inshallah.